Welcome to my channel. Today we are going to start a new series called the partial differential equation. In simple terms, we call it a PDE. So look at the definition of a PDE. A PDE describes the relationship between an unknown variable and its partial derivatives. Alright, so we are saying if you have an equation where an unknown variable has a relationship or describes the relationship between itself and then its partial derivative, then we are saying it's a partial derivative. The general form of a partial derivative is given as f brackets, we have x, y, then we have u, then we have ux, we have uy, we have uxx, so we can have uxx and then it can continue equal to 0. So here we are saying that x and y are the independent variables. They are independent variables. And then u in the case where I use red, u is the unknown function, and then ux, uy, and then uxx. They are all, so uxx, and then the remaining ones are all the partial derivatives. So in simple terms, that is the definition of a partial differential equation. Now let's talk about the order of a partial differential equation. All right, so we will define the order as simply the highest derivative in the equation, or the highest derivative that appears in the equation. So the order of a PD is simply the highest derivative that appears in the equation. So that is the definition for the order of a partial differential equation. All right, so an example is, so when we have ux plus uy equal to f of x y. In this case, we are saying that this one is order 1. Why? Because the highest order we have here is, this one is the unknown function is differentiated only once. Here the unknown function is differentiated only once. So that is the only highest differentiation that is appearing here. And so that we say order 1. So order 1, or first order. Then we can also have another example. So another example we can have is when we have uxx plus uy is equal to 0. In this case, we have u being differentiated 2 times in respect of x, and then u differentiated once with respect to y. So the highest order here is the second time that we differentiated x, and so this one is second order. All right, so if you are being asked to find the order of a PDE, simply the definition, the highest derivative that appears in the equation. All right, let's look at some examples of PDEs. Some examples of PDEs, some examples of PDE. All right, so we can talk about the transport equation. And then when we talk about the transport equation, it is simply given as, ut plus v ux equal to 0. This one describes the instance the transport of a solid pollutant is moving along a channel. So in a sea, or maybe in a river, how we transport pollutants is delicate, so we use the transport equation. And then here u is the concentration, and then here is the stream speed. So if it is in the stream that we are transporting the pollutant, then we can calculate using these ones. So that is that for that one. And then we have another example we will talk about, heat or diffusion equation. So we have the heat or diffusion equation. The heat equation is given as ut is equal to k uxx. And now this k is a constant which represents the rate of diffusion. But here you should know that the rate of diffusion cannot be negative. The reason being that if it becomes negative, that means that we are going to say the heat is moving from the cold region to the high region, which defy the sense of heat, movement of heat, right? Here U is the unknown function for the temperature, so U represent temperature, and then K is the rate of diffusion, the rate of diffusion. So you take note of this one. These are some of the examples. There are many partial differential equations. So another one we'll talk about is the wave equation. So the wave equation, and with the wave equation, it is given as utt equal to c squared uxx. So what does the wave equation do? It describes, for instance, the propagation of wave of small amplitude. When you play violin, then we are talking about that wave, that equation, the propagation of the waves of that small amplitude perfectly in an elastic cord. Yes, and then the U represents here, the U represents the wave. It may represent the wave amplitude. So it may represent the wave amplitude, and then the C represents the speed of propagation, of propagation. So these are some of the examples we can talk about. We have other examples like the Laplace equation. It's also a partial differential equation. All right. Now the last thing we'll talk about, or we'll speak about in this video, is the solution of a differential equation. Solution of a partial differential equation. So let me do that. Partial differential equation. That is a PDE. All right. So when we talk about solution, if we have a partial differential equation given to us, we are saying that a solution of the PDE is a function in terms of ux, uy, and uz. So it's a function, a solution of a PDE is a function u of x, y. It is in terms of the unknown function that satisfies the equation identically. So it satisfies the equation identically in, at least in some regions. It is not always that it will satisfy the equation in all aspects, but at least in some region it will satisfy the equation, at least in some region of xy, in some region of xy variables. Right. So we take an example of, and then we verify. So you are asked to verify that uxy is equal to 3x plus 4y all to the power 3, all to the power 3 plus 3 is a solution of the PDE. So that's what we want to prove. So we want to verify. So solution, what it means is that if, as the equation, the differential equation, the PD is given to us, we, if we substitute this particular value inside here, we are supposed to get 0. As in, if you differentiate this one with respect to x, and then you differentiate u with respect to y, and then you substitute it here, you are supposed to get 0. So that's what we do. So given u x y to equal to 3x plus 4y cubed all over 64 plus 3. Now ux, what will be ux? We'll get ux to be equal to, so ux will give us, so if I'm going to differentiate, this one drops. I have 3x plus 4y all over 64, square here. Now when I differentiate whatever is inside here, I'm going to get 3. And then when I simplify, I have 9 3x plus 4y squared all over 64. Then I'll do the same thing for uy. So uy is giving us, so we have 3 dropping. I have 3x plus 4y all squared all over 64. Then multiplying that by the differential of whatever is inside, that will be remaining 4. I'll multiply that, and I'll have that. So when I multiply, I have 12 3x plus 4y squared all over 64. Now I substitute these values back into the differential equation, and so I have 4 bracket ux, we had 9 3x plus 4y all squared all over 64, and then so minus 3. Then what do we get? We had 12 3x plus 4y all over 64, and this one is square. So and then when we do this, what are we going to have? We're going to have 36 over 64 multiplying 3x plus 4y squared, and then minus when we have 36, and then we have 3x plus 4y squared all over 64. Now you see that they are all the same, so we get 0. So hence we can conclude. So we say hence uxy equal to 3x plus 4y all over 64 is a solution. Is a solution of the given PDE. Alright. Thank you for watching, and see you in the next video. Bye bye.